All right, so this is 2-6 for Algebra 2. Our learning objective is to analyze transformations of functions. And our essential understanding is that there are sets of functions called families in which each function is a translation of a special function called a parent. So we've got parent functions, and we've got families of functions. It's good times. The linear functions form a family of functions. Each linear function is a transformation of the function y equals x. The function y equals x is the parent function, is the parent linear function. So we're going to be looking at a few families of functions. Don't write anything down until you get to a parent function. We're going to be looking at a series, like different families of functions. One of them that we're going to be looking at is the linear function. It's a very basic form. Its parent function is y equals x. A parent function, and so now you guys start your writing, is the simplest form in a set of functions that form a family. So for our case of y equals x, that's the simplest form of a linear function.
You're at the middle.
Yes. So everything after parent function you're going to be writing. A transformation. So with the function y equals a f of x minus h plus k is a change made to at least one of the values, a, h, and k. The four types of translations are dilations, reflections, rotations, and translations. So we are going to start transforming our functions either by multiplying, by replacing x with x minus h, or by adding a k value to the function. If you need a moment, I'm going to be moving on, but if you need a moment at home, go ahead and pause the video and write these definitions down. A translation. So we're talking transformations. Don't get these two mixed up, because a translation is a type of transformation. So a translation shifts the graph of the parent function horizontally, vertically, or both without changing the shape or orientation. So it just takes your entire graph, moves it left or right, or up and down. It looks, a vertical translation takes your entire function and either adds or subtracts a k value. A horizontal translation takes the x value out of your function and replaces it with either x plus h or x minus h, and that'll shift your graph left and right. We'll talk about specifically how that affects in just a moment. All right, so you guys are writing these example problems on your paper. We are going to look at how y equals 2x and y equals 2x minus 3 are related. How are their graphs related? The first way to look at this problem is by using what you know about linear functions. In this scenario, I know that the y equals 2x is a linear function, And I also know that y equals 2x minus 3 is also a linear function. All right, so y equals 2x. I know that my y-intercept is at 0. And I know the slope is up 2 over 1, since our slope is 2. So I can graph that pattern across my graph. Make sure that when you are graphing lines, that you actually use a straight line. I'm going to put it as close as I can. Okay. All right, and then this one, my next line, y equals 2x minus 3. I know that the y-intercept is at negative 3, and that the slope is up 2 over 1. And for time's sake, let's just make a copy of this line and throw it down. So as you can see, our first line is identical to the second line, except the second line is translated 3 units down. So this is 3 units down from my original one. So my original equation is y equals 2x, and y equals 2x minus 3 is translated 3 units down. It is not a coincidence that this is minus 3 and this is 3 units down. When you're shifting horizontally vertically up, it's going to be a plus the amount you want to go. And when you're shifting down, it's going to be minus the amount down you want to go. So when we look at B, what is the graph of y equals 3x translated up 2 units? So we're going to take our 3x and we're just going to add 2. And what that does is take all of our y coordinates and add 2 to it. You can also do this with a table. So if I take y equals, so I'm going to start at 2 on my y-intercept, and I'm going to go up 3 over 1. So this line is here. Its original line, I'll graph the original line for you so that you guys can see. Its original line is y equals 3x, so that would start at 0 and go up 3 over 1. So it's that same line, just parallel. And our original one is 2 units down from, or 2 units up from our original one is, we have our original one, and then our translated one is 2 units up from that. Okay, horizontal translation is the opposite if I want to move a function left or right, if I want to go right, I subtract from the inside of my function. If I want to go left, I add to the inside of the function. But let's do this problem. The graph shows the projected altitude f of x of an airplane scheduled to depart an airport at noon. So noon is our 0. If the plane leaves 2 hours late, what function represents this transformation? So if my horizontal transformation that we took notes on from the previous page says I take my function and I replace x with x plus or minus h. If I have a function f of x and I want to move everything over 2 hours, so I'm leaving 2 hours late, I'm going to replace my x value in my function with x minus 2. So it's going to push everything over. So it was 0, now it's going to be at 2. This was here at 1, now it's going to be right around 3. So it pushes everything to the right 2 units. So I want you to look. If I'm going right, it is minus. So minus moves right, plus moves left. And I remember because it is the opposite of up and down. Okay, so we're going to take a look at this scenario here. Suppose the flight leaves 30 minutes early. What function represents this translation? 30 minutes early means I'm going to move left. To move left, I add. Am I going to add 30 to my x values in my function? Nope. I am not going to add 30. It's a trick. What's the trick? Where are they trying to get you? Right, it's in minutes. This guy is in minutes. We are here in hours. 30 minutes is how much of an hour? Half. So we're going to add 0.5 to each of our x values. And then it's going to shift this entire function back a half an hour. So here we go. So I put that on the graph. So let me make sure this is going to work. All right, so we talked about moving up and down. We talked about moving left and right. Now we're going to talk about reflecting. So a reflection flips the graph of a function across the line, such as the x-axis or the y-axis. For any function f of x, to get a y-axis reflection, we are going to take out our x value and put in a negative x. That'll reflect everything across the y-axis. And just to recall, this is the y-axis. So it's going to reflect it across the y-axis. To reflect across the x-axis, you're going to take your entire function and stick a negative on the front of it. And that'll give you a reflection across the x-axis. And I'm going to show you what that looks like here. So for h of x, let h of x be the reflection of f of x equals 3x plus 3 in the x-axis. What is the function rule for h of x? So an x-axis reflection says I'm going to take my entire function throw parentheses around it and put a negative on the front. So h of x is equal to f of x multiplied by that negative 1. So that equals negative 3x plus 3. I'm going to distribute out that negative so I can simplify this down. It's negative 3x minus 3. I'm going to show you, let's say g of x is f of x reflected across the y-axis. So we're adding this component. We're going to find g of x, and he is f of x reflected across the x-axis. So if we follow our convention here, that is, we're going to take f of x, take out the x, and replace it with negative x. So here that would mean taking out the x value here and putting in negative x, and then simplifying. So that would be negative 3x plus 3. Let's take a moment and see what those look like graphed. So if you go to your graphing utility, so if you graph your original function, y equals 3x plus 3, you can see it's a nice line that lives right here. We're going to reflect it across. If you look at, we reflected it across the x-axis first. So we got negative 3x minus 3. And what it did is it took each of these coordinates and mirrored them across the x-axis. If you haven't used Desmos.com, it's amazing. So let's go ahead and we're going to turn this Mr. Blue off. And we're going to see what happens when we reflect it across the y-axis. So we take our function and replace the x value. So we get negative 3x plus 3. And you can see it reflects it across the y-axis. So every coordinate from over here, its new coordinate is now to the right, and it just switches. So if I folded this paper along the y-axis, it would meet up with its mirror reflection. So this was the x-axis reflection, and this is the y-axis reflection. All right, so we have been moving functions left and right, up and down, reflecting across the axes. What we're going to do now is we're going to stretch them tall and long or make them fat and skinny. So a vertical stretch multiplies all the y values of a function by the same factor greater than 1. If you don't have a factor that's greater than 1, you are not stretching it out all tall. And that's how I remember this. If I multiplied my height by 2, I would be taller and longer. If I cut my height in half, I would be shorter and fatter. So a vertical stretch multiplies your function by a value greater than 1, and a vertical compression reduces my factor, makes me shorter and fatter, by a factor between 0 and 1. So it's got to be a nice little fraction. And we don't include negatives because we just talked about negatives where? Up here. That's a different genre. So we just look at values that are bigger than 1 or between 0 and 1 when we're talking about vertical stretch, vertical compress. We don't talk about the negatives because we cover them with the reflections. It looks like this. Y equals A times f of x is a vertical stretch when A is greater than 1, and a vertical compress when A is between 0 and 1. All right, the table at the right, this table right here, represents the function f of x. What I'm going to do so we can visualize it a little bit better is I'm going to graph my function in blue. So when x is equal to -5, we got 2. -2, we've got 2. 0, we have -3. 3, we have 1. And 5, we have -2. That looks fine. Good times. For this function, what are the corresponding table and graph for the transformation h of x equals 1/3 f of x? So we're going to take all of our values and multiply them by 1/3. So 2 times 1/3 is 2/3. 2 times 1/3 is 2/3. -3 times 1/3 is -1. 1 times 1/3 is 1/3. And -2 times 1/3 is -2/3. So we're going to go ahead and graph h of x, and he's going to be in red. So at -5, we're going to be at 2/3. At -2, we're going to be at 2/3. At 0, we're going to be at -1. At 3, we're going to be at 1/3. And at 5, we're going to be at -2/3. So my new graph is going to be almost the same as our old graph, but just shorter and compressed. All right, so to summarize the information that we just talked about, to move our function f, we take our function and add a k value. To move our function down, we take our function and subtract a k value. To move it right, we replace the x in our function with x minus h, and that'll bump it to the right h units. To move it left, we take the x value in our function and write x plus h instead, and that'll move it left h units. To stretch it vertically, we take a number that's bigger than 1 and multiply it by our entire function. To compress it vertically, we take our entire function and multiply it by a number that's between 0 and 1. To reflect it across the x-axis, we take our entire function and multiply it by a -1. To reflect it across the y-axis, we take the x value in our function and replace it with -x. All right, so we are going to take these things and put it all together and find, because you don't just do one and not the other. We can apply actually all of these items to our function, which is exciting. Okay, so for our graph g of x, it is the graph of our parent function f of x equals x, stretched vertically by a factor of 2, translated down 3 units. What is the function rule for g of x? So we take g of x we are going to stretch vertically. So we're going to take our entire function and stretch it by a factor of 2. So I take my entire function, stretch it by a factor of 2, and then I'm going to translate it down 3 units. So I take my entire function and I minus 3 units. And that's g of x, the graph of f of x equals x, stretched vertically by a factor of 2 and moved down 3 units. All right, so let's look. We're gonna take it to the next level. We got f of x equals x squared. What transformations change the graph of f of x equals x squared to the graph of g of x equals x plus 4 squared minus 2? So we definitely know this minus 2 moves it down 2 units. But what does this plus 4 do? What does the plus 4 do? So you look, when I take out my x coordinate and I replace it with x plus h, we're moving it left 4 units. So the transformation that changed the graph of f of x equals x squared to the graph of g of x equals x plus 4 squared minus 2 is takes that value and takes our function and moves it down 2 units and left 4 units. Take a couple minutes and write down a summary. I'm going to leave this up here, so if you missed any pieces of this, go ahead and come up and you can toggle back and forth, left and right. If you toggle to the right, you'll get blank pages, but if you toggle left,